Good evening, everyone. So in the previous lecture, we had finished the electromagnetic induction, right? So today we'll be starting with the alternating currents, right? So we'll be discussing some basic terminologies with respect to the alternating current or AC currents. So how actually AC current is different from the DC currents, right? In the last lecture, we discussed about the AC generator, how actually the AC is generated. A basic concept of the AC was discussed, right? You can see in the last slide, we discussed the concept of periodic EMI. That's the periodic electromagnetic induction, right? Here we had a coil, right? And the coil had n number of turns, and there was an external magnetic field. And in presence of that external magnetic field, the coil was rotating with a constant angular speed, that was omega, right? And we calculated the EMF induced in a coil, right? The result we got, it was NBA sine of omega t, where omega is the frequency of rotation of this circular rectangular or the circular coil, right? And P is the external uniform magnetic field, and A is the area of this coil, and N is the number of turns, right? So it means that the EMI or the EMF that was induced in this coil was a periodic EMI because of the periodic function of this EMI, right? Induced EMF. It was an NBA sine of omega t. Sine function is itself a periodic function. So EMF induced is also here a periodic EMF, right? Or we say it as a periodic EMI, right? So now you can see some. If we plot this EMF with respect to time, right? If we plot this EMF with respect to time, right? Let's suppose this is E and this is the time t. The nature of this EMF will be sinusoidal in nature, right? You can see here at each and every instant, I can write the equation that E is equal to NBA sine of omega t, right? NBA sine of omega t. And we know that NBA is nothing, it's the maximum value or the amplitude of the EMF, right? It's the maximum value of EMF, or we can say that NBA is nothing. Let's suppose NBA is nothing, is the maximum value, or we can write it as Emax, right? It's the maximum value of the EMF, right? If this is the maximum value of EMF, right? If this is the maximum value of EMF, we can write this E as Emax sine of omega t, right? Emax sine of omega t. And if you plot this EMF as a function of time, it will be a sinusoidal in nature. It will be a sine function, right? Sine function of time. And you can see here, the value of the EMF is continuously changing, right? And it first increases from time t equal to 0 to the maximum, right? To the maximum. So at some time, let's suppose I call it as t upon 4, the value of the EMF is maximum, then the value of EMF decreases, right? And continuously and becomes 0 at this point. And the direction of this EMF, induced EMF, is now reversed, right? The direction of this induced is now reversed. Now, once again, it will be a maximum in the negative direction, right? And it will come back and become 0 after time t, right? Or we can say that this cycle of the induced EMF repeats itself after a fixed interval of time. And this fixed interval of time we call as time period, right? This fixed interval of time is called as time period. So you can see the magnitude of the EMF induced is changing, or we can say the magnitude of the current is changing, because we can write the current equal to EMF upon the resistance, right? E upon the resistance. Or we can write it as E max upon R sine of omega t. So this will be the equation of current, right? Or we can write this E max upon R as the maximum current. So I will be nothing. It will be I max sine of omega t. I max sine of omega t. Correct? It's sine of omega t. Now, so EMF here is continuously changing, and it becomes maximum, and then it changes its direction or reverse its direction periodically, right? So such type of currents we call as alternating currents, right? These are the alternating currents. So this is the behavior of the alternating current, right? So the magnitude is not a constant here, right? The EMF is not a constant. The EMF is variable, right? After fixed interval of time, right? The cycle repeats itself, right? After the cycle repeats itself, and after fixed interval of time or fixed time, the EMF reverses its direction after a fixed period, right? After a fixed period. You can see here the time period of this cycle is T. Capital T is the time period, right? So from here to here, the time period is T by 2, right? T by 2. Now from 0 to T, time period is T. So this is the half of the time period, right? So it means that after time T by 2, it reverses its direction, right? Now the EMF is in the negative direction, right? So this cycle we call as positive cycle of the EMF, and this cycle we call as negative cycle of EMF. Now similarly, in case of DC current, there is no such thing happening, right? In DC current, the current has a constant value, neither the direction change nor the magnitude of the current change, right? So such currents we call as DC current. So this is the behavior of a DC current, right? This is the behavior of a DC current, right? So in case of AC currents, we have different value of the EMF, different value of the current at different instants of time, right? But in case of DC currents, we have the constant value of the current, and the current does not change its direction, right, at all. So such currents we call as DC currents, right? So this was the important discussion with respect to the AC and the DC, how actually we can differentiate between the AC current and the DC current. First of all, AC currents reverses its direction or changes its direction, right? They change its direction. So second point is that the magnitude is not constant as in case of DC currents, right? So it has a fixed time period for the AC currents or the AC voltage. The time period is fixed. It means the cycle of the AC actually repeats itself after a fixed interval of time, right? So this is the difference between the AC current and the DC current, right? Now this term omega is nothing. Omega is nothing. This is what we call as angular frequency, right? Angular frequency. Omega we call as angular frequency. Angular frequency. And we can write this angular frequency as this omega, nothing, that will be equal to 2 pi times the frequency of the cycle, right? And the frequency is nothing, it's equal to 1 over time period, right? 1 over time period, correct? So this is the basic difference between the AC and the DC currents, right? So here are some of the more examples of the AC currents, right, or AC voltage. Let's suppose this is the plot between current versus time graph, right? It's a plot between current versus time. So I versus T, right? I versus T. You can see here. Now, once again, the magnitude of, let's suppose I naught is the magnitude of current here at this, at time T equal to 0. And after some time T1, right? After some time T1, now the current change reverse its direction, right? After some time T1, and the current is now once again equal to minus I naught, right? It's minus I naught. So after a fixed interval of time, you can see here the current reverses its direction and the cycle gets completed. Cycle gets completed after some time period T, right? And it continuously repeats the cycle. So you can see here the potential or voltage here is the AC voltage here is in the form of a square wave, right? It behaves like a square wave. So we call it as square AC, right? Square AC. So it's a square AC, right? It's a square AC. The time period for this AC is also fixed, right? Is also fixed. It reverses its direction after a fixed interval or after a fixed period, right? So maximum value of this current is I naught, and the minimum value, that's minus I naught in the negative direction, right? So it means that the magnitude of the current for the square wave remains same, that's I naught, right? It only reverses direction after some fixed interval of time, right? So this is the square wave, right? Square AC wave. Similarly, you can see here this triangular form of AC wave, right? Triangular form of AC. This also repeats its direction after fixed interval. That's the time period. So this will be the time period. If this is the time t equal to 0, this is t time equal to t, capital T, and this will be the time period for this AC, right? So you can see here, since AC here is in the form of a triangular wave, right? We can call it as triangular AC, right? It's a triangular AC. Triangular AC, right? And similarly, you can see here, this is a sawtooth form, right? It's a sawtooth form. This form of the AC we call as sawtooth, right? So once again, it repeats itself after a fixed interval of time, right? After a fixed interval of time, the AC, the magnitude of the cycle of the AC is repeated, right? And it also repeats its direction or reverses its direction after a fixed interval. So this is sawtooth AC, right? Sawtooth AC. So it's not necessary AC will be of the form of sinusoidal equation or the cosine function of time or the sine function of time, right? It can be in the form of square wave, it can be in the form of triangular wave, it can be in the form of sawtooth wave as well, right? So these are the different forms of the AC that we have, right? So, but generally what we study, we either study the, generally we study the sinusoidal form, cosine form, and sometimes we study the AC form as well, square wave form as well, right? So let's try to discuss different terminologies related with this AC, right? You know that if we, this is the sinusoidal function of current, right? With respect to time, I can write its equation as I is equal to I naught sine of omega t, right? I naught sine of omega t, correct? So you can see here, the maximum value of this, the maximum value of this current is at t equal to t by 4, right? At t equal to t by 4. So from here to here, the time is t by 4. From here to here, it's a t by 4, and once again from here to here, it's a t by 4. Once again, it's a t by 4. So it means the total time period comes out to be equal to t, right? So after a fixed interval, the cycle gets repeated. That fixed interval of time for the cycle we call as time period. So time period is nothing. It's a complete one cycle, time taken to complete one cycle of a AC current or AC voltage, right? That we call as the time period for this AC, right? And you know that frequency is nothing, angular frequency is nothing. We call angular frequency, that's the 2 pi times the frequency, right? 2 pi times the frequency, right? Or we can write it as 2 pi over t, where t is the time period, right? This is the angular frequency for this cycle. Now the question is that at time t equal to t by 4, right? At time t equal to t by 4, right? At time t equal to t by 4, right? The value of the AC current is maximum here, right? That's the maximum value of the AC current. I can write this maximum current as I naught, right? I naught is the maximum current. So if we substitute the value of t equal to t by 4 in this equation, right? So I is equal to I naught is the maximum value, right? Sine of omega. We can write omega as 2 pi over t, right? And the value of time is given as t over 4. So we can write it as t over 4. T and t will get cancelled. This and this will get cancelled. We'll be left with sine pi by 2. Sine pi by 2 is 1. So it means that I is equal to I naught. This is the maximum value of the current, right? But this is nothing. This is what we call as amplitude, right? Amplitude of AC current, right? So amplitude is nothing. It's the maximum value of current in either direction, or we also sometimes call it as peak value, right? We also call it as peak value for current. So amplitude is nothing. It's the peak value of the current or the maximum value of the current, right? So similarly, you can see this equation is a cosine equation where I is equal to I naught cos of omega t. You can write it as I naught cos of omega t, correct? So this is also an AC wave, right? AC current. So here we can see that at time t equal to 0, the current is maximum. The current is maximum, or I is equal to I naught, right? The maximum current here is, or the amplitude of the current here is at time t equal to 0, right? So this is the value of I naught, right? At time t equal to 0, the value of the current is I naught, correct? And the frequency, you know, it's the number of cycles completed, right? Number of cycles completed in a given time, right? So that's the frequency, right? Per second. We can write the number of cycles completed per second, right? That's what we call as the frequency of the uh, any object, right? Any object. So here it will be a frequency of this AC wave or the AC current, right? So this was with respect to the basic terminologies here, right? Now the question is that we can also discuss this omega t factor here, but we'll discuss this later, right? We'll write the general form of the ACs, right? AC currents, where we will discuss the concept of phase, initial phase, right? Total phase and all. That we'll be discussing later part of this chapter, right? Let's first focus on the basic terms, right? Basic quantities that we study in this AC currents. And one of the important concepts or the important terms that we study in this AC concept are the instantaneous values, peak values, average values, and the RMS values of a AC current, right? So these are some of the different quantities, right, of an alternating current that we have to calculate, right, in this chapter, right? So we'll be discussing all these quantities one by one, right? So instantaneous values are nothing. It's nothing. It's the value of the current or the value of the AC voltage at any particular instant, right? So it's nothing. It's the value of current or EMF at any instant of time, right? At any instant of time. So at any instant of time, what is the value of current or the EMF? We call that as instantaneous values, right? We call that as instantaneous value. You can see here we have a AC equation here. Find out instantaneous current value for I is equal to I naught sine of omega t at t equal to t by 8. Now, whatever be the value of this current at t equal to t by 8, where capital T is the time period for this AC wave, we will call it as instantaneous current, right? We will call it as instantaneous current because at different instants we have different values of the current, right? So we can write I is equal to I naught sine of omega t. And we have to find the value of this instantaneous current at t equal to t upon 8. We'll just directly substitute the value of time in this equation. We'll get the instantaneous current. That's I naught sine of omega is 2 pi over time period, right? Multiplied with the t. That's t over 8, right? That's t over 8. And this t and t will get cancelled. So it will be pi upon 4. So it will be equal to I naught sine of pi upon 4. Sine of pi upon 4 is sine of 45, right? Or we can write it as I naught over root 2. So this is the what we call as instantaneous value. This is the value of the current at time t equal to t by 8. This current we will call it as instantaneous current. Similarly, we have to calculate the if we have to calculate the instantaneous voltage, the equation is given as V is equal to 200 sine of uh, 400 pi t, right? 400 pi t, right? At t equal to 1 by 800, right? Now, if we look at the amplitude or the peak values of this voltage, right? Peak values of this voltage, you can see here the peak values of this voltage are. So I was equal to instantaneous current was equal to I naught sine of 2 pi over t, right? Multiplied by t over 8. So this was nothing. It was equal to I naught over root 2, right? I naught over root. Now we have this second question. We have to calculate the instantaneous voltage. That's V is equal to 200 sine of 400 pi t, right? Sine of 400 pi t, right? At time t equal to t over 1 over 800, right? 1 over 800 seconds. So this is the time at which we have to calculate the instantaneous voltage, right? This is the time we have to calculate the instantaneous voltage. Now look at this. Now, if we interpret this equation, the maximum or the peak value of this voltage is nothing V naught. This is the peak value, right? This is nothing. This is what we call as peak value, right? This is nothing. This is what we call as peak value. That's equal to 200, right? 200 is the peak value for this current, right? And the angular frequency is nothing. If we compare with this with the general equation, that's V naught sine of omega t. The omega value of omega by comparison will be nothing. It will be equal to 400 pi, right? 400 pi is the omega, right? If this is the omega, we can also calculate the time period from here. So time period is nothing. It will be 2 pi over omega, right? That's the angular frequency, or we can write it as 2 pi over 400 pi, right? 400 pi. This pi and pi will get cancelled. We'll be left with 1 over 200, right? 200 seconds. So this is what we call as the time period, right? But we have to calculate the instantaneous voltage. Instantaneous voltage we can directly calculate. That's P is equal to 200 sine of 400 pi. Substituting the value of t, that's 1 upon 800, right? So it will be by 2, right? And sine of pi by 2 is 1. It means it's equal to 200, right? So 200 will be the instantaneous, and this will be also the peak value for this AC voltage, right? So peak value for this AC voltage is 200, right? Now we have to we studied about the instantaneous values, right? Now we'll study about the average values, right? We studied about the instantaneous values and the peak values as well. Peak values are nothing. These are the maximum value, right? Maximum value of current or EMF. Maximum value of current or EMF, right? These this is what we call as peak value, right? Maximum value of current or EMF, right? Now becomes important. Now what is important is the average values, right? How we define the average of an AC current, right? AC voltage or AC current. So what actually it signifies, right? So average current is nothing. The mean value of an AC or any half cycle, right? Is that value of DC which would send same amount of charge, right, to a circuit as is sent by the AC through same circuit, right? It means that if this is the DC current for the half cycle, right? If this is the DC current, if this is the DC current for first half of the cycle, let's suppose this is current versus time. This is first half of the cycle, that's the positive half, right? And this is the second half, that's the negative half, right, of the cycle. So this is the positive half, right? This is the positive half. You can see here the amount of charge for this time t equal to t by 2, right, whatever charge we send through the circuit, right, by this AC current from time t equal to 0 to t by 2, it means that for half a time period, right? If we calculate the average of this AC current, right, over the half cycle, right, over the half cycle, or the mean value of this AC current over the half cycle, then if we send the same average current to the DC circuit, the amount of charge that will flow in the DC current will be same as that has flown in this AC current, right? So that's how we define the average values of AC current and the DC current, right? So we'll be calculating different averages, right? Average for different time periods, right? So let's suppose that this is the sinusoidal equation that's equal to I is equal to I naught sine of omega t, right? We can write it as I naught sine of omega t, correct? Now, if we have to find the average of any function, right? Be it any function, we can define the average of any function as it's nothing, it's integral of function f of x dx, right? With the limits x1 to x2, right? Upon integral of dx with the limits x1 to x2. So this is how we calculate the average of any function, right? And this is how we represent an average, right? So for any function, be it time, be it current, be it EMF, be it any other function, right? Be it velocity, acceleration, whatever, right? We can calculate the average of any function using this integration, right? So this integral will give us the average of any function, right? Similarly, if we have to calculate the average of this sinusoidal function, right, between the given time period, let's suppose we have to find the average of this sinusoidal function for the complete time period, right? From 0 to t. So we have to calculate the average of this sinusoidal function. If we calculate the average of this current, I equal to I naught sine of omega t, right? The current is I is equal to I naught sine of omega t. Now we have to find the average value of this current for the complete cycle, right? For the complete cycle. So what we'll do is that the average of this current will be nothing. It will be integral of I naught sine of omega t, right? Dt with the limits 0 to capital T, because it's for the complete time period, right? Upon integral of dt with the limits 0 to capital T. So we can calculate the average. So it will be I naught integral of sine of omega t dt with limits 0 to t upon integral of dt will be nothing. It will be t. So we'll be left with here time period t, right? We can rewrite it as I naught upon t, right? The value of sine of omega, the integration of the sine of omega t is nothing. It's cos of omega t, right? Omega will be here. It will be cos of omega t, right? With the limits 0 to t, right? 0 to t. 0 to t. Now you can see here you can see here cos of omega t with the limits. So it will be I naught upon t with omega here, right? Multiplied by, if we substitute the value of the limits, so it will be cos of omega. Omega is nothing, it's 2 pi over t, and upper limit is t. We can multiply here t, and the lower limit is 0, or it will be cos of 0, right? Cos of 0 degree. And you can see cos of 0 is 1, and cos of 2 pi is also 1, right? Cos of 0 is 1, and the cos of 2 pi is also 1. So it means that this equation will be equal to 0, right? Or we can say for a complete cycle, for a complete cycle, the average of this current, AC current, is nothing, it's equal to 0, right? So for a complete cycle, the average of sine omega t or cos omega t is 0 for both. You can see also from this diagram, if we are calculating the upper portion of this integral, right? For the upper portion of this integral, you can see here, this integral actually represents area under the curve, right? This integral represents the area under the curve, right? So this will represent actually the area under this current time graph, right? Area under this current time graph. You can see the positive area is actually equal to the negative area. It means the total area will be equal to 0. If the total area is 0, so the average has to be equal to 0, right? So the average of this AC current, average value of this AC current for the complete cycle, will be equal to 0, right? Now we have another concept, what we call as root mean square value of current, right? Root mean square of current. So root mean square is, once again, how we define the root mean square. It's the value of DC which would produce same heat in given resistance in given time, as is done by the alternating current when passed through the same resistance for the same time. It means that if we pass a resistance, right? If we pass the resistance, if we pass a current, or if we pass a AC through a resistor, right? AC through a resistor, right? And for some time, right? For some time. And if we calculate the RMS value of this AC and pass that RMS value of the current as DC in the same resistor for the same time, then they will produce the same amount of heat. That's what this definition says, right? It means that, let's suppose this is the resistor here, right? This is the resistor here. Let's suppose this is the resistor here, right? This is the resistor here of resistance R, and we are supplying an AC, right? We're supplying an AC. Let's suppose for some time t, the RMS value is there is some RMS value for this AC, right? There is some RMS value for this AC, and there is AC current flowing through it, right? And for that time, this AC will produce some heat through this resistor, right? Now, if we pass the same RMS value of the current, right? Same RMS value of the current as DC through the same resistor for the same time, right? As DC through the same resistor for the same time, then the heat generated, if heat generated here is H, then the same amount of heat will be generated here also. So that's what we say, that's how we actually signify the RMS value of a current, right? So there are different ways to calculate the RMS value of the current, right? We'll just try to learn how we can calculate actually the RMS value of a current, right? How we can calculate the RMS value of a current. So RMS value we studied as root mean square, right? Root mean square, right? Root mean square. So we can say that RMS value is nothing. Let's suppose if we have to calculate the IRMS, right? IRMS. What we will do is that we'll just first square the current, right? We will first square the current, right? If we square the current, then we'll calculate the mean of this current. We calculate the mean of this current, right? And then take the root of that mean, right? Take the root of that mean. So this is nothing. This is the root mean square, right? This is nothing. This is the root mean square. Root mean square value, right? It's very important with respect to the ACs, right? Root mean square. So root mean square is nothing. You just first take the square of a function, then take the mean of that function, and then once you calculate the mean of that function, then take the root of that mean, right? Take the root of that mean, you will get the RMS value. That's the root mean square value, right? That's the root mean square value, correct? So let's try to calculate the root mean square value for this current I, right? Let's try to calculate the root mean square value for this current I here. So you can see here the value of I is nothing, it's I naught, right? I naught sine of omega t, I naught sine of omega t. So we have to find the RMS value, right? We have to find the RMS value. First of all, what we'll do is that we'll just take the square of this current. We have taken the square of this current, that will be equal to I naught sine square omega t. I naught sine square omega t, right? I naught sine square omega t. Now, once it is done, we have to calculate the mean of this function, right? We have to calculate the mean of this function. We know that how we actually calculate the mean of this function. This is how we calculate the mean of any function, right? We're using the same technique, right? To calculate the mean of this function, we'll just take this mean of this function for the complete time period from 0 to t, right? I naught. So it will be I naught square here, right? I naught square sine square omega t, right? Sine square omega t dt, right? Upon integral of 0 to t will be the limit dt, right? So we'll get mean square value as mean square value. Sometimes you are asked to calculate the mean square value only. So at that time you have to just square the function and take the mean of that function, right? So that will be the mean square value, right? So mean square value is not same as that of RMS value. Mean square value has different is a different thing, and RMS value is a different thing. So for mean square value, you have to just take the square of the function first, then take the mean of that function, right? So it will be I naught square. It's a constant, right? We'll take out of this integral. So it will be integral of dt upon t. So it will be t here, right? So it will be t. Will be left with integral of sine square omega t with respect to t, right? Integral of this from 0 to t. Now, how you will calculate the integral, right? You can just convert this sine square omega t using the equation, right? So it will be, now we know that cos of 2 omega t is nothing. That will be equal to 1 minus 2 sine square omega t, right? You can replace the value of sine square omega t here as, if you replace the value of sine square omega t here as, so it will be 1 minus cos 2 omega t, right? Over 2, right? Over 2, over 2, over 2. So this will be the value of sine square omega t. You can substitute the value of this sine square omega t in this equation, right? Then integrate it with the proper limits. The average of any sine square omega t or cos square omega t comes out to be equal to half, right? It comes out to be equal to half, right? So it comes out to be equal to half. So the value of this will be actually t by 2, right? So it will be actually equal to t by 2. So I square average will be equal to I naught square t over 2, right? Multiplied by t. So this and this will get cancelled, right? If this is the value of mean square, right? This is the value of mean square. So the value of the mean square is nothing. Mean square has the value equal to I naught square over I naught square over 2, right? I naught square over 2, right? Then to calculate the RMS value, what we have to do, we have to take the root of it. We have to take the root of it. We'll take the root of it. It will be root of this mean square, right? That will be equal to root of I naught square over 2, or we can write it as I naught over root 2. So this will be the value of the RMS, right? This will be the RMS value, right? So RMS value for the complete cycle for this function, for this current, that's I naught sine of omega t, it's nothing, I naught over root 2. I naught is the peak value of this current, and divided by the factor root 2, right? Divided by the factor root 2. So this is how we can calculate the RMS value for the different functions, right? Similarly, if we have to calculate the RMS value, right? Let's suppose for half the cycle, right? If we have to calculate the RMS value for half the cycle, right? If we have to calculate the RMS value for half the cycle only, right? For the positive half cycle only, right? So this will be I versus T, right? For the positive half cycle, what we'll do is that we'll proceed in the same way. We'll take the square of the current, right? That will be equal to I naught square sine square omega t, right? Sine square omega t. And then we'll take the mean of this function, that's this, right? and mean is taken as I naught square sine square omega t, right, dt over integral of dt. Now the question is limits, right? Since we're calculating for the half cycle only, the limit will be from 0 to t by 2, right? 0 to t by 2. So we'll change the limits from 0 to t by 2, right? 0 to t by 2. 0 to t by 2. So once you calculate this integral, then take the root of this function, average of this square value of this current. Take the root of this, we'll get the value of the IRMS, right? For the limits 0 to t by 2. So this is the value of the IRMS, right? Root means square current, right? So let's try to one important point about sine square omega t and cos square omega t is that the average value of sine square omega t or sine square theta, right? In general, sine square theta, right? For the complete cycle, it's equal to 1 by 2, and the average of cos square theta is also equal to 1 by 2 for the complete cycle, right? For the complete cycle. So that's equal to 1 by 2. We can remember this factor here, right? So the average value of sine square theta is 1 by 2 and cos square theta is 1 by 2. So similarly, the average of sine square omega t is nothing. It's equal to once again 1 by 2, and the average of cos square omega t will be also equal to half, right? It will be also equal to half, correct? So let's now try to solve this question, right? Find RMS value of current where current is given as, we have to find the RMS value of current is given as I is equal to 3 plus 4 of sine of omega t plus pi by 3, right? Omega t plus pi by 3, right? So what we'll do is that we'll just square this first, right? We'll square this first. Let's square it. So it will be 3 plus 4 sine of omega t plus pi by 3, right? Whole square, right? Whole square. Now we can expand it, right? As a plus b ka whole square. So it will be a square, that's 3 square, that's 9, right? Plus b square, right? It will be 16, 16 sine square omega t plus pi by 3, right? And then there will be a factor of 2ab, right? 2ab factor. So it will be 2 into 3, right? That will be 6. 6 into 4 will be 24, right? 24 sine of omega t plus pi by 3, right? Omega t plus pi by 3. Omega t plus pi by 3. Now we have calculated the square value of this current. We have to now calculate the mean of this current, right? Then we'll take the root, right? So the mean of this value will be nothing. It will be the mean of this, right? Right? So it will be mean of 9, and it will be mean of this 16 sine square omega t plus pi by 3, right? And it will be the mean of this factor, what we call as mean of this factor as well. That is mean of 24 sine of omega t plus pi by 3, right? It's mean, right? And one more important point to note here is that mean of sine of theta is equal to 0 for the complete cycle, right? And the mean value of cos of theta is also equal to 0 for the complete cycle, right? For the complete cycle. So there are two important points. The mean of the sine square theta is half. Mean of the cos square theta is half, right? For the complete cycle. For the complete cycle. So, and for the complete cycle, mean of sine theta and cos theta is actually 0, right? Now you can see mean of 9, it's a constant, so it will be as 9, right? It will be as 9. And the mean of sine square omega t plus pi by 3, there's a constant 16, we'll take it out. And the mean of sine square theta is half, right? It's half, you can write it as 1 by 2, plus we'll be left with mean of this sine omega t plus pi by 3. And we know that mean of sine theta for the complete cycle is 0. So it means the mean of this term will be equal to 0, right? We'll be left with this only, right? So it will be 8, right? Or that will be equal to 8 plus 9 is nothing. It's 17. So this is the mean square value. And if we take the root of this mean square value, right, we'll get the RMS value. That's IRMS, right? IRMS. So RMS value of this current is nothing, it's root 17. The root 17 is the RMS value for this uh, given current, right? Root 17 is the RMS value, right? Similarly, we can find the RMS value of these currents as well, right? We have to find the RMS value for these currents as well. We can find the RMS value one by one for each of these currents. Let's begin with the part first, right? Let's begin with the part first. So for the part first, the current is given as I is equal to A plus B sine of omega t, A plus B sine of omega t. We have to find its RMS value. So for calculating the RMS value, what we do, we take the square first, then take the mean, and then take the root, right? Then take the root. So this is how we can calculate the RMS value, right? So first of all, we'll square this current. It will be I square, right? It will be A plus B sine omega t square, A plus B sine omega t whole square. So it will be A plus B whole square. It will be A square plus B square sine square omega t, right? Plus 2AB, right? 2AB sine of omega t, right? This is our square value. Now we have to take the average of the square. So this is the symbol of average. So if we take the average of square, we have to take average of A square. We have to take the average of B square sine square omega t, right? Each and every term. We have to take the average of 2AB sine of omega t, right? Each and every term, we are taking the average of each and every term. Average of A square will be nothing. It will be A square only, right? It will be A square only. So B square, it's a constant, so it will be taken out of this average, right? And average of sine square omega t is nothing, it's b over 2, right? It's 1 over 2. And we know that average of sine theta is once again 0. So this term will go to 0, right? So its average will be equal to 0, right? So this is the value of the average of current square, right? This is the value of the average of current square. This is our I square, right? If this is our I square, then taking the root value, right? Taking the root value, our IRMS will be nothing. IRMS will be nothing. That will be equal to root of this value, right? And it's nothing, it's under root of A square plus B square over 2, right? So this is the RMS value for this current. Under root of A square plus B square over 2 will be the RMS value for this current, right? So this is how we can calculate the RMS value for the different functions, right? Let's now discuss this part second. Similarly, for the part second, we can see that for the part second, if we calculate the RMS value, we'll first write this current I, that's equal to A sine omega t, right? A sine omega t plus B cos omega t, right? B cos omega t. First of all, we'll take the square of this current, that's I square, right? I square, that will be A sine omega t plus B cos omega t, right? P cos omega t, right? The square of these currents is nothing. That's equal to A square sine square omega t. It will be A plus B whole square plus P square cos square omega t, right? And then 2 times A P sine omega t cos omega t, right? Cos omega t. We can rewrite this equation in the form, you know that twice sine omega t cos omega t. It's nothing, it's 2 sine theta cos theta, right? 2 sine theta cos theta, we know that it's nothing. It's equal to sine of twice theta, right? Sine of twice theta. So we can write it like that. So I square will be nothing. It will be equal to A square sine square omega t, right? Plus B square cos square omega t, right? So it will be AB sine of twice omega t, right? We have reduced it to this form, right? Now we have to take the average, right? Just take the average. We take the average, we have to take the average of each and every term, right? Here, each and every term. We are taking the average of each and every term here, right? So you can see that the average of sine square omega t is half. So it will be A square over 2, right? Average of cos square omega t is once again half. That will be square over 2. And once again, we know that average of sine theta is 0 for the complete cycle. Similarly, average of the sine of 2 theta will also be 0 for the complete cycle. It means this term will once again vanish. It will go to 0, right? It will go to 0. So this will be the value of I square, right? Mean of I square, right? Now we have to take the root of this mean of I square, right? To calculate the RMS value. That will be our IRMS. That will be our IRMS. So the IRMS is nothing. It's under root of A square plus B square over 2, right? So this is the RMS value for this current, which is given as A sine of omega t plus B cos of omega t. This is how we can calculate the IRMS value for this current. So that's it for today. In the next lecture, we'll be discussing about the phasors that will be discussed tomorrow. So till then, take care and goodbye.